The author of your textbook goes through first order reactions in this next section that we're ready for, and then he covers second order reactions in the following section. I'm going to cover both of them in the same video because what I want to do is I want to compare and contrast them so that you can hopefully really get a decent understanding of the similarities and the differences between the different orders of reactions. We're also going to talk very briefly about the zeroth order reaction, although he never covers it in the book. I am going to cover it because it just makes sense to me to look at all three of them together. So on the board behind me, I have a number of different graphs and equations, and don't be overwhelmed at the amount of stuff that's up here because I'm going to narrow that down and say, okay, here's the piece that you need to know. But I'm going to go through and I want to explain the different pieces of it so that hopefully you'll be able to understand the differences between them. We've already looked at a general graph of what happens when as a reaction proceeds, how the concentration of reactants decreases over time. How that looks on a graph depends on the order of the reactant, whether it's zeroth order, first order, second order, which you've already gotten some experience with. You have the lab that you did for this chapter, you saw that one of the reactants actually was zeroth order. It didn't matter when you changed the concentration of the hydrogen ion, it didn't make a difference to the rate of reaction. So that reactant, though it has to be there for the reaction to take place, the concentration of it didn't make any difference as far as the reaction rate. And so that's the situation with a zeroth order reaction. And in that type of reaction, the concentration of a first order reactant simply goes down in a linear fashion according to time. So this is a linear graph. And the graph of this equation looks like this, okay? Now, in a second order reaction, we see the type of graph that I had on the board before, where the reaction goes down, or as the reaction proceeds, the concentration goes down, but you can see that this curves, and that as this gets less and less concentrated, the reaction rate slows. The same thing is true for a second order reaction, but, and I don't know how good you can see this in my drawing, but what I was trying to show you is that here in the second order reaction, this line drops off a lot more quickly than it does over here, okay? And if you recall, part of that is because when you have a second order reaction, as the reactor concentration would double, then the rate would quadruple. And so therefore, that explains why as the concentration goes down, the rate goes down so much faster as well. So between a first order and a second order reaction, the decrease in the concentration of the reactant is more rapid for the second order, and the decrease in rate is also more rapid than it is in a first order reaction, okay? Now, to get to the next line down on my stuff here up on the board, you have to understand calculus, and you have to be able to do a bunch of calculus. And I know a lot of you, either you may be currently taking calculus, maybe you're not taking calculus at all. No worries, you don't have to understand calculus to understand what I'm going to put on the board. I'm just not going to derive where all this came from, okay? We can do some things to these equations, obviously, to make the graph look different. So up here, I simply have a graph of concentration of the reactant versus time. If I do what's called an integration, which again, that's calculus and you don't need to understand it, but if I take the natural log of the concentration of the reactant and put it over time, this now becomes a straight line for a first order reaction. And the equation for this, while it may look similar to this one now has an E in it with an exponent, which is a result of having a natural log up here, okay? And this is the equation that he gives you in your textbook to calculate how far along a reaction is, what the difference in concentration is going to be. And so this is what he gives you. Another way to rearrange this same equation is to look at it in this form. And in this form, this actually takes the algebraic form of y equals mx plus b. Now, if you look at this, hopefully this will make sense. Log of the concentration is what's graphed on the y-axis. So there's the y, okay? Time is what's graphed on the x-axis, so there's x. The natural log of A, and that little zero down there means that's the initial concentration of A. Well, that's what's going to be at time equals 0, so that's the initial concentration, so that's the y-intercept. And so therefore, the slope of this line is going to be the constant, rate constant for the reaction, except it's going to be the negative of it, okay? So this piece right here, this negative k and this m, this is something that you're going to be using in the lab that you're going to be doing on the simulation that I sent to you. And it's going to be a couple of days till you do it, but this is the piece that you're going to need out of that. And so that's part of the reason why I'm going through this, is to help prepare you for that lab that I'm going to have you do. Okay. Now, to relate this to the half-life that we did in the section before, again, you have to put in some substitutions and do some algebra, and he does that for you if you're interested in that. But this is the equation to find the half-life, to find the rate constant, to find out what the half-life is going to be. Okay. Now, if I look at the same thing with the second order reaction, if I take the inverse of the concentration of the reactant and graph it according to time, I again have a straight line, but it's going to go the opposite direction, okay? This is the equation for that line, and this is another one that he gives you in the book, but I can take this equation and I can rearrange it, and once again, once I rearrange this and get this, I'm going to have the form y equals mx plus b. And so again, to point it out on the graph, 1 over the concentration is what I'm graphing, so that's my y. T is on the x-axis, so it makes sense that that would be the x. 1 over the initial concentration is going to be right here at time 0, so that's the y-intercept, so that makes sense that that's b. So again here, the slope of this graph is equal to the rate constant, okay? And the equation for the half-life for a second order reaction is this, and you'll notice it's different than the first one. Again, that's because we're doing an inverse as opposed to using a natural log and having an e involved in there, okay? The summary of all this then is that for a first order reaction, the concentration is exponentially related to time, whereas in a second order reaction, the concentration is inversely related to time. All right. So what of all this do you need to remember and understand? Well, the equations that he gives you are this one and this one and this one. Okay. So put those on an index card and you will be able to use those on your test. I don't expect you to memorize those. This concept and this concept you will need for the lab that you're going to be doing. So you're going to need to look at these concentrations and go, all right, where is the rate constant for this? Well, it's the slope of this line. So you'll need to, you don't have to memorize this or have this on your card necessarily, but you will need these relationships for the lab that you're going to be doing. So that's why I went through all this. The other thing that you need to really have a handle on is what these graphs look like. Whoops, not this one. So the 0th order, this one is a straight line. For a first order, this one is a straight line. And for the second order, this one is a straight line. Okay, so once you do a kinetics experiment, you can manipulate the data to come up with several different graphs, and then that graph will tell you, is this a first order reaction, a second order reaction, a zero order reaction? Whichever one gives me the straight line is the one that tells me which order that reactant is going to be. Okay, so again, that you're going to use these graphing methods and these forms of these equations for your lab, but these are these equations here are the ones that you're going to need to know. As far as your test, put those on an index card. You can use the index card on the test. Okay, there are half-life equations for all three. The first order reaction is the only one that we're really going to be working with, but I put them down there because I wanted you to know that yes, they do exist. Okay. All right. Example 11.3, I'm going to go ahead and run through that one just to help you see the math, since there is natural logarithms and exponents and e's and all that kind of stuff in it. So example 11.3, and I'm actually going to stick it over here because that's about the only empty place on my board. So example 11.3. The catalyzed decomposition of hydrogen peroxide is a first order reaction. The initial concentration of hydrogen peroxide is 1 molar and the rate constant is 0.0693 per second. What is the concentration of hydrogen peroxide 25 seconds later? Now, this is pretty much a plug and chug. If you use the equation that he gave you, again, I'm just going to go through it so you can see what we're doing with these reactants, or with these E's. Get this worked out right. So the concentration, so I'm going to use, this is the equation that I'm using right here. So the final concentration is what I'm being asked for. The initial concentration, they said, was 1 molar. And then I have an E to the negative KT. Well, they said K was 0.0693 per second. And then the time that I was given was 25 seconds. Okay. Now you'll see that what happens here is that this second and this second cancel out, leaving me with no units. So what that then gives me for the next line is 1.0 molar times E to the negative 1.73, 3 significant figures because of what I had up here. Okay. Then when I take E to that exponent, I have 1.0 molar times 0.18, 2 significant figures because I had 2 after the decimal point here. And then the final answer turns out to be 0.18 molar. And you can see that the units worked out. Okay, so there's example 11.3. Example 11.4 in this section, again, is just a simple plug and chug. If you've got the equation for the first order half-life, you're just going to plug the numbers in, chug the answer right back out. And he didn't give you an example for the second order. Okay, so that was a lot of information, I know. And again, part of it you're not going to need to necessarily understand, but hopefully I boxed the things here to help you understand what you do need to write down. I will step out here at the end of the video in case you need a second to get a full view of everything that's on the board, in case you want to pause it and copy something down if you didn't already copy it down. And then hopefully that will get you well on your way to not only doing the problems in the next couple of sections, but also will prepare you for the online simulation that you're going to be doing 2 or 3 days from now. I'll move out so you can copy anything down that you need to and get a full view of the board. So you can pause the video there if needed. And other than that, I will see you a few days from now.